Here's an electron bound to a hydrogen atom. We know the atomic energy levels are discrete.
Right. Discrete means that the electron is only allowed to have certain amounts of energy. All other energy amounts are forbidden. So here's another energy level, and here's a third allowed energy level. But how do we calculate the energy values for an electron in an atom? How do we find the values of E1, E2, and E3?
By pretending the electron is trapped in a 1D box.
But aren't these two scenarios physically different?
Yes, in a box, the electron only has kinetic energy.
But in an atom, the electron also has potential energy.
Here are our notes so far.
So I understand that the electron can have different kinetic energy values while in the 1D box over on the left. And we're going to use the 1D box energies to approximate the atomic energies on the right. But are those kinetic energies on the left discrete, like E1, E2, and E3 on the right?
Yes, it's shocking at first, but I'll prove that the electron can only have certain allowable kinetic energies in the 1D box.
Okay, but last question before we start. How can we treat these two different physical scenarios the same?
The box and the atom have just enough similarity for a rough approximation.
That makes sense. In both cases, we don't know exactly where the electron is, and the allowable energies are discrete.
That's right. In both cases, the electron has many possible positions. Let's get started. First, we'll draw some psi waves.
Did you say sideways? But why do we draw psi waves? Aren't we looking for energy values? Psi waves only tell us about the electron's possible positions.
You're right, but we can use these psi graphs to find the electron's wavelength.
Oh, and once we know the wavelength, we can find the kinetic energy.
Here's our method for finding our energy values. Let's complete step 1.
Let's draw those psi waves. How do we start?
The starting point is this. The electron's psi probability waves must be standing waves. The electron has no chance of being found outside of the box. Thus, the probability, and psi, goes to 0 at the edges of the box. Let's show that by adding points here and here.
Those look like nodes. I'll add them to the other graphs, too.
The first standing psi wave looks like this.
Oh, I get it. We're just drawing in standing waves for psi. The next two standing waves look like this and this.
Great! Now let's find the wavelength.
The first graph shows half a wave cycle, so the length L of the box is equal to lambda over 2.
The second graph shows a full cycle contained within the distance L, so L equals lambda. The third graph shows 1.5 cycles in the distance L, so L equals 3/2 lambda.
Right, and the subscripts 1, 2, 3 just show that these are the first, second, and third standing waves. Let's take these three equations and write one general equation. We could add a 1 here without changing the first equation. We can add 2 over 2 here without changing the second equation. And now we notice a pattern. The 1 out front in the numerator matches the subscript. Likewise for the second and for the third equations. If we want to write a general equation for some wavelength n, the nth wavelength, it'll look like this. When we solve this equation for lambda sub n, that means isolate lambda sub n, it looks like this. That's a really important equation which we'll have to memorize.
Great work so far! This is the general equation for the nth wavelength. We're done with step 2.
So let me try and see if I can write down the energies. Here's the equation for lambda, the nth lambda. But we've already learned de Broglie's hypothesis, which is that the wavelength of an electron is related by this equation to the electron's momentum, p. If I isolate p in this equation, it looks like this. But we're talking about certain allowable values of lambda, and we call those values lambda sub n. Lambda 1, lambda 2, those are the allowable wavelengths. Because there are allowable wavelengths, there will also be certain allowable momenta, p sub n. We can write this equation again, but we can replace lambda sub n with 2L over n. And then we get this. And now we know what the relationship is between momentum and kinetic energy. So if there are only certain allowable values of momentum, then there will only be certain allowable values of the energy. We can take the same equation and replace the momentum with this expression. When we distribute the squared and simplify, we get this. That is the final equation that we were going for.
This general equation gives us all of the energy levels that the electron can have when it's trapped in the bottom of the 1D box.
And only certain energies, E1, E2, E3, and so forth, are allowed because only certain wavelengths and momenta are allowed in the box.
Quiz on this next class.